Today, I'll be presenting on a unique topic, a project I was interested in a while back that crosses both data science and politics, specifically the concept of gerrymandering. I'll try to do the topic a bit of justice. We'll go through a bit of the politics, the concept of gerrymandering, and the applications of data science to it, as well as the limitations, specifically in America, where it's a problem. So let's go through a bit of background in politics. We all remember how big the US elections were with Biden versus Trump. And that's actually just one of three important elections. The legislation branch of the government, like most democracies, even in Trinidad, is made up of three components. The presidency, which is a type of figurehead at the top, and then Congress. So think about it as our parliament. And that normally falls into a bicameral system, meaning it has two chambers, the Senate and the House. So the lower house, for example, it develops bills for taxes at a more local or regional level. And after it's approved, it goes up to the upper house for debate. And if it's a matter that needs it, then to the presidency. And it's similar to like an ETL pipeline in a company where a small hiccup at one point could result in a long wait further down the line, which is why bureaucracy tends to have like long time lags to get things done. It's inherently built into it. So we're going to focus on the lower, the House of Representatives, because at this level, we get the most direct representation. So the House is made up of 435 representatives, and that is something ratified at a previous time, almost 100 years ago. And it's not really subject to change, falling into a historic and cultural political room. Even in Trinidad, we have 43 seats, and that was set 2007, and that's not subject to change. So with the 435 seats, for 51 states, how do we apportion it? They use exclusively population density as at that point. So every 10 years, based on the census, they look at the states that have the largest populations and apportion the number of representatives relative to each other. And as you'd expect, dense states like California, for instance, could get a huge number, 53, 52 in this diagram, while rural states that are even larger than California will get much fewer. So you'll have a more diverse group in these dense states, and they could vary geographically, so city to city. So they need more representatives, so it makes sense to have this system. So how do individuals join the House? It's based on voting, kind of. Most democracies like America and the states within it implement something called a first past the post or winner take all system. So essentially the person with the most votes wins. And that system has inherent flaws such as minority rule, or it tends to converge to two-party systems over a period of time. But we'll just accept this type of voting and move past that. So you will vote for your specific House representative based on where you live. So if you fall within a specific territory, you will vote for the representatives for that district alone. So simple enough. But who decides what district you live in? So recall that the number of House reps will change every 10 years based on the census. So if you fall into a city that had like a technological revolution or it modernized and the population rose rapidly through migration, you might go from having one seat to 10 in your state. So now they have to cut up that state into 10 segments and you will be assigned to one. But which one? The process for redistricting is not documented. It occurs behind closed doors and it's up to the politicians or the party in power at that time. So depending on how you draw those lines, you could possibly get an advantage. And this is where gerrymandering is, where a politician could pick the voters they have. So consider the following situation in Bird Bagel. You have two parties and the people vote along them. You have Hummingbird and Parrot. So let's say that they're distributed and each block will represent 100 voters in each block. Depending on how I cut it up, you can get different results. So for the first one, we'll cut up the population into straight lines. So you have 8 parrots, 7 hummingbirds. It's almost a 50 to 50 ratio with parrots slightly ahead. So if I cut this up into some rectangles, as you can see, as you can see here, you have a 3 to 2 in favor of the parrots. And that kind of preserves the relative slight majority that the parrots have. But if I decide to cut this up in a different way, so if I redraw it in favor of the parrots, you could set it up so that a small lead could overpower it. So here I just decide these last two columns, I'll make parrots in favor. So now you have a 4-1 split on the seats, so 80%. You previously had near 50-50 population split in the votes, and now you have an 80% winning in seats. And this is just a very small example. You can see how really large states where you have multiple census blocks could get out of hand. And it'll get more extreme in terms of the shapes. So the first instance of gerrymandering was done by the former Vice President Elbridge Gerry. His redistricting lines were actually made into a cartoon by the newspaper, which likened it to Salamander. And they just combined the names gerrymandering like that. And since that time, the instances of extreme gerrymandering have increased. So in 2012, the elections with several key states were accused of gerrymandering. And it's kind of easy to see why. You have a near split voting for the seats, almost 50-50, but the amount of seats won were like 28 to 72. And then if you actually look at the shapes for the districts, you can see that's very far off. But you can't go into a court of law and say, all right, these shapes look a bit weird. We want to redo the drawing for it, because you could argue for and against it. So if we take a look at Illinois 4th specifically, you could make the case that the top portion here, I'm not sure if you can see with the pointer, the top portion here and the bottom portion, you have two Hispanic communities that will vote along the same line. So this, whatever shape it is, might actually be viable because it meets the two laws that you need for a district. You need an equal population and you need to have it continuously, which this technically is. So most research in this field will fall along two lines specifically. They will look into how to measure gerrymandering first, and identify the instances of excessive gerrymandering, or they will look at methods to generate the lines for the districts. And that could fall into a bunch of topics from optimization to graph theory. A recent project done by CSU looked into measuring gerrymandering. So first they can try to identify the instances of excessive gerrymandering for a court, and then they could take the required steps to fix it. So they used two metrics that they developed: partisan symmetry and efficiency gap. Partisan symmetry refers to the relationship between the votes won and the seats gained. So for instance, if you have 50% of the votes, you should get 50% of the seats. And it's fairly easy to validate. If you switch the votes, so from parrot to hummingbird, if they had 4 seats before and the other team had 1, if you switch the votes, it should be 1 to 4. But if parrots won the first election, you switch the votes and they still win the election, then you have evidence that gerrymandering occurred. And you could supplement this with any type of statistical test, so like two-sided t-tests or anything along those lines. Another way you could evaluate is with the efficiency gap. So this counts the number of votes that each party wasted in an election to determine whether a party enjoyed a systematic advantage over another. So votes wasted is essentially, if you needed a certain amount of votes to win, based on the amount of population you have, any of the excess ones above that. So if you needed 50% of the votes to win and you gained 60, 10% of those votes would be votes wasted. And with these metrics, they decided to apply it to a combination of electoral, geospatial, and demographic data. And they used georeferencing to create a shape file. So that represents all the data at the smallest granular level, which is called a census block. And working with this file, it's not feasible to go through every possible iteration for the map. So for instance, a 7x7 block is a few 100 million, a 9x9 is 700 trillion, a 10x10 block that they ran was 1 month of MIT supercomputers. And then a real practical example would be almost 400,000 by 400,000. And the time to compute that is more time than has existed. So instead they use sampling. And specifically, they use a recombination technique that they had proposed. So you have this initial map that you draw. You try to combine 2 regions. So let's say the blue and the yellow. You get this one singular region. You create an adjacency graph out of that and find the spanning tree within it. So the minimum spanning tree. So you have your adjacency graph here, and then you find the spanning tree within that. Once you find this spanning tree, you look for the spot where you can break it such that each of these 2 parts will have an equal population. And then with that, you can generate 2 new regions. So you have a new blue and yellow region. And then you repeat this for a billion, a million, maybe maps. And then you can plot that so that you can get the distribution of how the votes would have been and how the seats would have been won. So in their instance, if you start off with a map like this and you have 1.5 seats won by someone, if you keep redistricting using the algorithm, that falls somewhere within the normal distribution. But if you started off with a map and they won 6 orange seats, so parrots won 6, and then you redistribute it, and you see that 6 is way outside the normal, then you have evidence that this was a gerrymandered map. Another example we could go through is by Wendy Tamcho, who is one of the leaders of reform of redistricting in the US. In her approach, they used evolutionary algorithms supplemented with spatial characteristics to improve the solution quality and computational performance with large-scale spatial partitioning applications. And that is a mouthful, and that paper is also extremely long, filled with about 7 different algorithms that they came up with recently. Essentially, they took a version of the evolutionary algorithm, the classic one, and introduced something called spatial operators so that they could better capture characteristics. So normal evolutionary algorithms would now be able to capture geometric or spatial data accurately. And as it scales up, it becomes computationally expensive. So I wouldn't go too much into depth with this one because it's an extensive paper, but it is interesting. And I advise anybody who's interested in graph theory to go through this. But the results for their new version of the evolutionary algorithm was the best performance when compared to the other heuristics in fitness difference, so the difference between the input and the ideal, as well as fitness in general, and path length, which is the location offset compared to the best solution. And one interesting thing they had was that if you notice in the second graph, there's like this massive drop off for everything. It shows that at like about 1,200 iterations, the population becomes either homogeneous or there's a change in the search issue for it. But the issue with this approach is that even though it performs really well in comparison to other heuristic algorithms, it is weakly scalable. So it doesn't lend well to a court case that you could set up if you want to challenge gerrymandering. The legal requirements for applying data science in a court would see that data needs to be open source. The algorithm needs to be open source. Whatever algorithm you develop needs to be non-partisan, so you have no bias to anyone. And it needs to be low computational intensity, so that if a judge wants to run it on the day, he should be able to prepare maybe a week in advance, if so much, but he should be able to run the algorithm on a laptop. And that's not necessarily a difficult set of requirements, because if you were to go on Kaggle or GitHub or anything, there is no shortage of algorithms or applications fit. Actually, one interesting project that I'd come across was by a chemist named Brian Haidat, a PhD in material science, who was just interested in projects. So he decided to dive headfirst into it for about 2 years and come up with an interesting solution. So he used Markov chain Monte Carlo simulation. And essentially, he used a randomly assigned set of districts to be drawn almost by hand, and using something called overnoid tessellation, which is just dropping a bunch of random points onto the map. You can assign each pixel to the closest point, and you can generate these borders. And it looks essentially like you would look at the edge of each border and then decide if you want to flip it, and then compare certain characteristics. So the characteristics he used for this were population density, fairness, so if you are keeping in line with how the votes actually ran, as well as shape, strangely enough. So he wanted to make sure that the shapes are not extremely odd in terms of their surface area and parameter. And then you keep repeating this process over and over. So you'll flip one pixel, you'll compare the maps based on these characteristics, so shape, fairness, and population density. And then if the map is better performing, you'll keep it. If the map is worse performing, you'll also maybe keep it. So he has a random number generator essentially that will determine whether or not you'll keep the bad map. And the reason for that is, if you start off with just some random set of points, you might find the optimal for that random set of points, but that might not be the best solution possible. So by exploring all the worst maps possible, you can come to some feasible solution later down the line. And in some instances, when he did this, the initial conditions, so the random set of points, could overpower what you would ideally want in an optimal solution. And you get maps that have some kind of similarity. So in this case, for, I believe this is Pennsylvania, the long piece at the end tends to come up in almost all of his maps that were generated. Right. And in terms of this, so fair representation, that's just a running tab of the actual outcome. The population density, you can compare that across districts, and he used a variation standard deviation. So instead of using squared, he used to the 4th power. Shape, he modeled it similar to energy. So in his words specifically, the further away a pixel is from the center, the more energy intensive it is to have it as a different voting. So if, for instance, and we'll see it here when this runs. Oh. Oops. Right. So at this point, you'll see that it starts to fuzz out a lot and leak into other areas. By making it energy intensive, you make the simulation more likely to flip those pixels back and maintain a kind of circular shape. And by tweaking the numbers for both the population density, the fairness, the shape and whatnot, you can actually make it so that you can have an equal population, but you can change the political outcome for it. So in the first instance, it was 2-11 in terms of the districts for the chairs. And you'll notice it has a fairly round shape. You have no strange things leaking out into each other. You repeat it for an 8-5, so a fairly balanced one. And it comes out a similar shape. So it meets the requirements for equal population. And then you can repeat it for 6-7. So regardless of meeting the requirements for population, shape, and fairness, you can change the outcome for a gerrymandered district so you can get either party to win depending on how the data looks. So by solving the issue for gerrymandering within the facets of law, so within population and the distribution and whatnot, there is no way to prevent that you can abuse it essentially. And there's no way to prevent that, but by making it openly accessible and easy to run, you make it verifiable to the general population, and you can make that possibly admissible in court. So this is one of the reasons why it's currently an unused solution in the legal system. But then that's further compounded by the data itself. So when you have a lack of fine-grained, consistent data, or if the data varies in granularity from state to state, if you want to apply an algorithm, the performance will vary. The generalizability and the acceptance it wouldn't hold. And furthermore, if you're looking for some kind of optimal, you could come up with any different amount of metrics or algorithms, but then you have to argue, not just logically, but politically for which one is better than another and how it varies from state to state. And on top of that, we all know that published papers, you'll always have something with that incremental improvement. So every year another paper will come out, we improved upon this algorithm by 1% this year or by 5% this year. And then having to continuously modify the political system for that might not hold up. And then past that, you also have a last set of challenges that go to the underlying assumptions. So we already skipped past the voting, but the first past the post voting, first past the post voting, the optimal number of districts you can also challenge. And then the one that I was interested in for the project was the value of a vote. So the underlying assumption is that every person has a vote and every person is equal when they are voting. But that might not hold up because each person is affected differently by laws based on like income level, social equality, and any number of factors. So you can possibly compute a different way for redistricting based on the value of each person's vote, which is one of the projects I was actually looking into. So this is just a few of the issues revolving around data science in the gerrymandering field. And with that, I'll take any questions.
Yeah, thanks for that, Aqeel. Nice presentation. So did you jump into this because of the issue in Tobago? Is that something you could analyze as well?
Tobago is just a strictly fictional example that bears no similarity to any real place. But actually, I was more interested in applying it in America specifically, because I have a few friends that live abroad and they do political activism and whatnot. And this was a viable project because they have a large amount of data. The voting value one was the specific project I was interested in.
But isn't it the case that we have to add some seats to Tobago or something? I don't know too much about it, but there's something going on in Tobago as well, right?
Yeah, based on how they have because I believe the electoral map for Tobago is split into 2 seats right now, and they're planning on adding more and whatnot based on disparities between how they vote. But if there is data available for that, you could do a project like this for Tobago or even Trinidad.
All right, because the issue was they had an even number and it was evenly split, right?
Mm-hmm.
And so they want to make it odd, right? Or something like that?
Something like that. They wanted to adjust it so that they wouldn't have this issue. And it would better represent the amount of people that voted for PDP, I think it was, versus PNM.
Okay. All right, no, but interesting stuff. Thanks.
Yeah, interesting stuff there, Aqeel. I was wondering though that in some of the stuff that you displayed before, there didn't seem to be any, or the authors didn't really seem to present anything like a spatial autocorrelations kind of thing to verify whether their initial thesis of gerrymandering was valid or not.
When you say to validate whether it was valid or not, you mean in terms of?
So take Pennsylvania. Okay, well, I guess we could accept that gerrymandering takes place now, right?
Yeah.
But like going back to some point in the past where they're able to do like a simple test, like
analyze the previous district lines and verify whether or not that was
well, it's more about the to detect if there's any regression spatially. Like typically when we think of regression, it's just points on that you're trying to fit. But if you add the spatial component of like, okay, a voter in this district is more likely to have voted one way or the other, is there a correlation between where they are, where that voter is coming from? So you add the spatial component, and you typically do a spatial lag or autocorrelation or something like that. There's like these statistical tests from Moran. I was just wondering if there was any kind of.
Not from and I've only read like about 10 papers on the topic so far. Right?
Okay, cool.
But in only 3 of the papers, they looked at spatial analysis specifically, but I don't believe either of those 3 did spatial autocorrelation.
Okay, cool. All right, no problem.
Possibly.
Right there. Yeah, there's an interesting page. I'll just share it in the chat. This one kind of looks at the Brexit vote and leave versus not leave kind of thing. Might be along the same lines.
Okay.
Cool. Thanks.